This lesson, we're going to finish up with implicit differentiation by looking at tougher horizontal and vertical tangent problems, as well as looking at second derivatives of these crazy-looking graphs. And then we will start introducing the next half of this unit, which is calculus word problems. Okay? So here we go. Let's start with this question. Find the xy locations of the horizontal and vertical tangents to this. Well, we need to find the derivative. We need to set it equal to 0 or see when it's undefined, just like we did last unit, just like we did on our quiz today. So let's do that. Make sure we use the product rule for the derivative in the middle. Make sure we have equals and the derivative of the stuff on the right side, which is 0. Pause here. I'm just going to go straight to the derivative. I mean, you can subtract 2x, you can subtract y. I'm going to then factor out the dy dx, leaving the x plus 2y. Here's the finished product. If you've done enough of these, you'll be able to go straight from your derivative step to your solution step. I wouldn't advise it for more complex derivatives, but for this one, you can just say, okay, minus 2x minus y, divide by the x plus 2y because you're factoring out. Okay? All right. Horizontal tangents. We know it's when the derivative equals 0. If I have a fraction, all I need is the top of the fraction to equal 0. So I'm going to set the top of my derivative equal to 0. And I have negative 2x minus y equals 0. Now, the problems that we had last lesson and on our quiz today, we'd usually be able to solve this. X equals 3, y equals 2, and then we would plug in to find the other halves. But if you look at this situation, I have two variables. I have 2x and y. What am I going to do now? Any ideas? Discuss. Yes. Yes. Yes, yes, yes. We have two equations, right? So all of the points on the graph of this, which is an ellipse, need to, have this characteristic where x squared plus x times y plus y squared equals 27. And all the points of the horizontal tangent need to have these characteristics. Well, we have a system. We have two equations with two unknowns. What do you think we should do to solve this system? Solve this guy for y. It's easy to solve this guy for y. I get y equals negative 2x. Well, I'm going to take that guy and substitute it into this guy. So let's go ahead and do that. So wherever I see a y, it's going to be replaced by negative 2x. So I got x, I got negative 2x. I got y squared. This is important. Substituting, you are replacing y with negative 2x. Y is being squared. So that means the entirety of negative 2x is being squared. Some students, when they substitute, they write negative 2x squared, and then they don't square the negative 2. That's wrong. Okay, so make sure we substitute in using parentheses. This equals 0. All right, well, let's start simplifying so we can solve. We got negative 2x squared. We got positive 4x squared here. Combine the 4, the negative 2, and the 1. That's 3x squared. Sorry, I don't know why I have equals 0. We're using the original equation, not the derivative. I have 3x squared equals 27. I can divide by 3. I get x squared equals 9. And then we know I get x equals plus or minus 3. Okay? All right. Typically, when we have half of what we're looking for, and we want the xy coordinates, we'll plug that back into the original equation, right, to get the other half. But that would be a lot of unnecessary work, and you might actually get an answer that's wrong. Well, one of them is going to be right, one of them is going to be wrong. There's an easier way to get the y coordinate for these x coordinates. Discuss with your neighbors. What would be the easier way? Anybody? You got a system of equations, right? 2 equations. I used one, plugged it into the other, boom. When we have a system of equations, do we have to plug back into one of those 2 equations specifically to get like the other point? No. Like we remember from like algebra 1, if I have x plus y equals 7, I have 3x minus 2y is equal to 5. Let's say I found a solution for x. Do I have to plug it into this one? No, I could plug it into either, right? Well, here's my system. This equation and this equation. I could plug the 3 and the negative 3 back into either. So let's plug it into the easier one. And I get 3, negative 6, and negative 3, positive 6. Let's do the same thing, you guys do it, to find the vertical tangents. Vertical tangents, we want no run, we just want rise, so we set the bottom equal to 0. It's probably easier to solve for x here, and then substitute that into the original. The system. We start to see things look very familiar to us. Now my y coordinate is 3, my x coordinate is negative 6. My y coordinate is -3. My x coordinate is +6. All right, so here's my horizontal tangents. Here are my vertical tangents. And these are the tougher horizontal and vertical tangents types of problems, where you have a system, from your derivative equal to 0, solve for a variable, plug it into the original. Let's look at the graph of this ellipse. Oops. Glad I'm recording. That was our practice problem. This is the ellipse of x squared plus xy plus y squared equals 27. Now notice, if I plug 3 back into my original equation for x, my original equation would have given me 2 y's. One y up here, one y down here. Only one of which works and is a horizontal tangent. That's why we don't want to plug it into the original, because it'll give me a erroneous solution. Instead, we plug it into the secondary one, the one that we used to substitute into the original. We got 3, -6 right here. Is a horizontal tangent. We got a vertical tangent at 6, -3 right there. We got a vertical tangent as -6, 3, and we got a horizontal tangent at -3, 6. Okay, pretty cool. All right, moving on. We will be asked to find second derivatives of implicit equations, like x squared plus y squared equals 25. Well, why would I take a second derivative of one of these equations? Why do we take second derivatives in general? Please remind yourself and your neighbors what we learned from last unit about second derivatives, what they tell us about graphs. If you said concavity, good job. The sign of this tells the concavity of something like that, whatever equation we're looking for, okay? All right, well, how are we going to take the second derivative of this? Just like we take the second derivative of a normal function. We would take the derivative twice. However, I have some recommendations. So we're going to take the derivative the first time. Okay? We could take the derivative again right now, but it's tricky. Okay, I'll show you what happens if I take the derivative again right now after we do it the way that I would recommend. Instead of taking the derivative right away, I'm going to solve for dy dx. Subtract 2x, divide by 2y, just like we've been doing, we get -x over y. Because I can cancel those 2's, right? It's nice if we can cancel. All right. Now, after we've taken the derivative and solved for dy dx, we will take the derivative again. Now, after a little bit of simplification, we'll take the derivative again. Now, you've probably been wondering, though I've told you, why is it d squared y over dx squared? You know, why isn't it like dy squared over dx squared? You know, second derivative, like why are the 2's where they are? Well, let's look. If I use kind of the idea of multiplication when I'm taking the derivative, you got d times dy. D times d gives us d squared. So that's where the d squared y comes from. That's why the 2 isn't over the y. Now you're probably thinking, well, Mr. Messner, if it's d squared y, why isn't it d squared x squared? Or why isn't it dx squared? Well, it probably should be, but it is just notation. So mathematicians are like, I don't want to write those parentheses, so I'm just going to leave out the parentheses. So that's where this notation d squared y over dx squared comes from. Okay? So taking the derivative of dy dx gives me d squared y over dx squared. This equals, let's use the quotient rule to take the derivative of negative x over y. You guys can do that. Quotient rule, please. Making sure that the derivative of y is dy dx. Making sure you have the bottom being squared. Careful, careful, careful. It's just going to be here. So the derivative of the top times the bottom minus the derivative of the bottom. So that side. There we go. Yes. So for the right side, we got negative x over y, the derivative of negative x, negative 1 times y, minus the derivative of the y, dy dx, times negative x, all over the derivative of the bottom, which is the y squared. Okay, so this is my second derivative. This is correct. However, I want to be able to use this and to kind of use it to analyze the concavity of my original graph. What would be a problem that you see in the state of this second derivative that's preventing us from being able to plug in just like simple xy's? Yeah, we got a dy dx on that right side. Okay, this guy I want to get rid of. Okay, that way I can work with this second derivative. Okay, this is an important step. And you can't just erase it, but I would want to get rid of it. How can I get rid of it or replace it with something or do something like that? Any ideas? The quickest that any class has figured that out. Since dy dx is equal to negative x over y, I can take that and plug it in right there. Okay? This is an important step. Replace dy dx with what it's equal to. Or substitute for dy dx. Okay, that brings me to d squared y over dx squared equals negative y minus negative x over y times negative x over y squared. And if you stop there, you're good. This is correct. All right. Now let me show you, if we go back to the original, we got the derivative. Let's see what happens if I took the derivative of this step before I solve. I'm going to just throw it over here. So this would be taking the derivative 2 times in a row. We can just watch. So I get the derivative of 2x, which is 2. The derivative of 2y dy dx. Guess what I'd have to use? Product rule. I'm going to use the product rule, thinking of 2y and dy dx. Okay, so I'd get the derivative of 2y, which is 2 dy dx, times dy dx, plus the derivative of dy dx, d squared y over dx squared, times 2y. That's equal to the derivative of 0, which is 0. Now, can we kind of see how this is kind of funky? And I'd have to do 2 plus 2, and I'd have to replace this with negative x over y, replace this with negative x over y, and then I'd have to solve for d squared y over dx squared. And, you know, I could do that, but it's more substitution. This would end up being 2x squared over y squared. I don't even know if this is going to be correct. It's got to be correct. And then negative 2 minus x squared over y squared over 2y. What was our derivative? I don't know if those are the same. I mean, I can multiply, and we're going to show how we can simplify this. This would be 2y squared over y squared. So it would end up being like negative 2y squared minus x squared over. So this would end up being 2y cubed as a denominator. The 2's, though, why isn't there a 2 with this guy? Yeah. Oh, there should be. All right, this is the same, okay? So you are going to get the same thing. And you'll see if we simplified, we would end up with this, or without the 2's. If you'd like to do it this way, you can. However, again, like you have to use the product rule with a dy dx. Derivative first times the second, derivative of the first times the second plus the derivative of the second times the first. You'd have to substitute in maybe more than one time, potentially. So you'll get the same answer. However, I would recommend solving for dy dx and then taking the derivative again. Okay? Now, I'll show you how this is equal to what we just got the other way. So this is totally fine, but watch what I can do to simplify this. So this is fine, good. This is all simplified. Going to combine the negative x and the negative x. And I get negative y minus positive x squared over y squared. So far, so good, right? Okay. I'm going to combine my two terms in the numerator. I'll put this y over 1. I'm going to multiply by y over y. And I get negative y squared over y minus x squared over y, but it's a common denominator, so it's negative y squared minus x squared over y. Over y squared. Now we could probably start to see how this looks just like what we just had on the other guy. I know that I don't have to divide by y squared. I can multiply by 1 over y squared. And then all of a sudden, boom, it shows up. We have negative y squared minus x squared over y cubed. Okay, which is what I got doing the other way after a little bit of a simplification. You don't have to get here. Okay, you could have stopped here. This is fine. But watch what I can do to simplify this even further. You think we're done here? We're not done. You might think, oh, divide both terms by y cubed? No. I'm gonna do this. And yep, that is a nice, easy second derivative that I can work with. Is anybody going to ask how I got that? Or is it obvious to all of you? Yeah? Mr. Peterman, you got it? No, you don't know how I turned from negative y squared minus x squared into negative 25? It's a good idea. It's a good thought, right? But nope, it's not that. Did anybody see it? Yeah, the original. Good job, guys. I can tell a lot of you actually saw it, and usually it's just 1 or 2 per class. So we are on top of things today. This guy right here must be true for all of the points on our graph. So I can actually use this, just like I use dy dx to simplify, I can use my original equation to simplify. Well, factor out a -1. This is positive y squared, positive x squared. X squared plus y squared, 25. Isn't that cool? It will end up happening with the second derivative for all these, yeah. And if you do the homework problems, the book always simplifies, sometimes wildly, to get the second derivative. And so like lots of steps. This is extra credit if you get here, okay? This is full credit. You got that? Now, but what's great about this is that it's easy to work with. So like, if I have a y value that's like 1, okay, it's something that's positive, and I plug it in, I got negative 25 over 1, that's going to be negative. A second derivative that's negative. What is that telling you? The original graph is concave down. Okay, so when y is positive, second derivative is negative, my graph must be concave down. Let's think about a circle. Sure. And this is a circle, radius 5. When y is positive, so when I'm up here, my second derivative is negative, concave down. When y is negative, my second derivative is going to be positive. When my second derivative is positive, we're concave up. Look at the graph. We're concave up. So this kind of confirms kind of what we did last unit, all about concavity, and second derivative signs tell us about the concavity of the original function. Okay? Why don't you guys find the second derivative for this equation? Either way works if you would like to do it, either taking the derivative 2 times in a row or taking the derivative, solving, and then taking the derivative again. And I want you to attempt to show that the second derivative equals 3x over 4y. Okay, take the derivative. If you'd like to, you can take the derivative again. However, be careful. You got to use the product rule with the dy dx. A lot of people don't do that. So instead, solve for dy dx, then take the derivative again. And then attempt to simplify. remember to substitute in what dy dx is equal to. And this is totally satisfactory. We are good. We can stop there. Make sure you get there. The rest is just fun, right? Fun. Let's go ahead and start simplifying this. 2's cancel. 3x squared would be 9x squared over y. 9x to the 4th over y. What am I doing? Common denominator. All right. Why don't we all pause when we get here, make sure we understand how to get here, and then let's start calling on you guys. What do you think we should do now to simplify? You can factor out a 3x if you want to. Sure. I probably would just do something right away. Just a moment. Yes. So now let's go back to this original equation. And let's plug in x cubed in for y squared. And now I get 12x to the 4th minus 9x to the 4th, which is 3x's to the 4th, over 4y cubed. Man, I feel like I'm really there, but I'm not. I want you guys to show me that it's 3x over 4y. Who can give me one more idea? What do you think, Mr. Mogam? Brilliant. We can either rewrite x to the 4th as x cubed times x, or we can write y cubed as y squared y. Right? Y squared times y is y cubed. And then I can replace the y squared with an x cubed, just like I did it before. I get 3x to the 4th over 4 x cubed y. 3x's cancel. You get 3x over 4y. Isn't that crazy? You should see some of the homework problems with the second derivatives. You should see how the book, it's like, how do you go from here to there? And I'll pretty much tell you, don't worry about it. All right, this is just fancy and fun, right? Right. Math is fun. Calculus is fun. All right. That's it for implicit differentiation, though. Tangents of random curves, second derivatives of random curves. We are going to now shift over to the rest of this unit, the second half of this unit, which is calculus word problems. We will call them related rates problems. Related rates. Okay? Okay. Well, we are comfortable with taking the derivative with respect to x of y. And we know that we say this is dy dx. Now, what does it mean? What does that d stand for? Yes, instantaneous change. So instantaneous change in y over an instantaneous change in x. Change in y, change in x. What does that mean to you? Slope. Okay. So understanding that d means instantaneous change, and we have an instantaneous change over an instantaneous change of y and then x, we know this translates to be tangent slope. And for most of the problems that we've been doing, we've wanted to find a tangent slope. But actually, not all the problems that we've been doing have been asking you about tangent slopes. Okay? And, you know, we're comfortable with this. This is 3y squared dy dx. And if you wanted to, with x, we could use this kind of notation and do the multiplication. We could have said this is dx over dx, which again is just 1, but you know, usually you go straight to 1. You don't realize that you could have written it as dx over dx. We are going to now take derivatives with respect to a different variable t. T standing for time. Now, if I take the derivative of y and I have dt down here, let's look at that notation again. The d would go with the y, the dt would go with 1. This would turn into dy dt, not dy dx. Now, the t is time, but its dt would be an instantaneous change in time, or like at a moment, like when a stopwatch gets stopped. You know, that's what we're going to be talking about here. This no longer is tangent slope. This is change in y over change in time, or how much are my y's changing at a specific moment in time. No longer tangent slope. How fast I'm going up or down, or how fast the y's are changing at a moment in time. Now, the derivative of y cubed, no longer 3y squared dy dx, it's 3y squared dy dt. And man, all of our derivatives of x's have always worked out nicely, but now it's not the case. Since I have a dt, I would not write this as 1. I would not write this as dx over dx. It's now dx dt. And now this has its own meaning. dx dt would be how quickly my x's are changing at a specific moment in time. It is now with the derivative of t, where d dt gives us dt over dt. That's 1. Now you have some space underneath these to do this, but turns out we've been doing this already. When I gave you position functions, time was a factor, okay? You were given a function for position. That means like at a specific time, you could tell the position by just plugging in the t, okay? And that's like where you're located. And I said, take the derivative. Well, if you thought that the entire time we were taking the derivative with respect to x, you were actually wrong. The entire time we would take a derivative, it would be with respect to t. That would give me x prime or dx dt equals 2t minus 2. And if you think about it, how quickly my x's are changing, how quickly my position's changing, that gives me the velocity. Okay, my position's here at this moment, and then just a split second later, it's here. I know I'm moving left at that rate. Okay, so this is change in position at a specific moment in time, or change in my x distance, x location at a specific moment in time. Okay? All right, well, now if I'm taking derivatives of x's and y's, it's not like what we did just last class or even just this class. It's different because I'm looking at how things are changing at a moment in time. I now will not say the derivative of x squared is 2x. It's 2x dx dt. The derivative of y squared is not 2y dy dx, it's 2y dy dt. Why don't you guys write the derivative of xy? It no longer is 1 times y plus dy dx times x. It is now dx dt y plus dy dt x. And now we're going to be looking at different equations of different things that could have x's, y's, and z's. We are going to start looking at formula like volumes of spheres. And we are going to be taking derivatives of these. Start with this one on the left. Yep. If you're thinking, do I have to write dz dt? Yep. Okay. Now, starting next class, I'm going to give you these word problems. And the word problems are like the following. You got a spherical balloon. I'm blowing air into it at a rate of 20 cubic centimeters per second. How quickly, how fast is the radius changing in terms of like units, centimeters per second? How fast is the radius changing at the moment when the radius is 3 centimeters big? Okay? That's the situation. And if I give you that question right now, you're like, oh my goodness, how are we going to do this? But we know the volume of a sphere is this, and you'll be given that, okay? 4/3 pi r cubed. we can use our friend, the derivative with respect to t, and all of a sudden, what would be the derivative of v? dv dt. What does this stand for? How fast the volume's changing. Yes, exactly. How fast the volume's changing. That's important. Okay, so this stands for how fast the volume's changing. Well, I told you how fast the volume's changing. I'm blowing air at 100 cubic centimeters per second or something like that. And then we'll have 4/3 pi, and then 3r squared dr dt. What would dr dt stand for? How fast the radius is changing. And we are going to use the information from our word problem, and all we're going to do is plug it in to this, and we're going to just solve for what we're looking for. The situation I just spoke out, I'd find how fast the radius is changing. I would plug in what this number is, and I'd plug in what this number is, and I would just solve. Not hard at all. Seems like a very complex problem, but it's not bad. Now, before we go into the word problems, I'm going to give you 3 examples of what we're going to be doing, but with everything laid out for you. Okay? I'm going to give you the formula. I'm going to tell you what you're trying to find and give you information. Okay? So, question.
So for what you're going to here, so basically it's going to be this but in word form?
Yes. Yes. Next class it'll be this but in word form. Yeah. And you'll have to make sure that you write this down correctly. You'll have to make sure you understand that you're trying to find this, and then you're going to make sure you write down this correctly. Okay? And that all gets translated from the problem, and you'll be fine. Don't worry. All right, so I want to find dy dt. Do you see a dy dt anywhere here? No, but discuss with your neighbors. What do you think you could do so that you had something with a dy dt in it? Take the derivative of your equation with respect to t, and all of a sudden, you'll have a dy dt. Let's start by doing that. All right, now, again, trying to find this. But look, I'm given this. Well, that goes here. And look, I'm given this. Well, that goes here. Okay. What's your answer? It's -1/6. Good. Just make sure you plug in all the stuff and see how you got the -1/6. Easy, okay? Plug it in. Solve. Do the next guy. Now let's see. Does this guy have an extra bit of difficulty? All right, first, pause. After you take the derivative of this, do you notice that you got a 2 here and a 2 here? Could you divide everything by 2 and get rid of those 2's? Yep. Okay. Now, we're told dxdt is 5. Okay. dxdt, 5. Not sure about x yet. Trying to find dy dt when y is 3. So y is 3. I'm trying to find dy dt equals 0. This is what I'm trying to find. They didn't give us x. Gosh, problem's wrong. Something's wrong. You're supposed to give us x, Mr. Messer. I said no. Gave you all that you needed and nothing more. Figure out with your neighbors, how do you find that x? You can solve for x, but I want to find dy dt. I want to solve for dy dt. Yeah, but I got to find x. How do I find x? Anybody got it? Yeah, but then I'd have like d, like you're saying take the derivative again? No, then I'd have d squared y over dt squared. I don't want that. What do you mean?
Like, it'd be x equals square root of 25 minus y squared and then plugging the y.
You always go like a step too far, but it's always correct. Use the original equation. If y is 3, could you find what x is when y is 3? Yep. All right, find what x is when y is 3. Okay, you should get plus or minus 4. However, you are told that our values for x are only going to be positive. I don't know if I have that in your notes. I do. Okay. So what we will be dealing with are changes in distances. Like we got 2 people running the bases in a baseball game. One person's like halfway between first and second running at this speed. The other person's halfway between second and third running at that speed. We're always going to make sure we're using positive distances there. But the question will be like, how quickly is the distance between the 2 people changing? Great problem. We'll get there. All right, so we're not going to use negative values pretty much moving forward. But now that I got that x is 4, we will, I don't want to say we're not going to use negative values. We may see some negative values out there, but when we're talking about distances, we won't. We'll use the Pythagorean theorem most of the times when we're talking about distances. We will subtract the 20, divide by 3. Got it? Yeah. Okay, now that we are prepared to do this extra teeny tiny little bit of work, you guys can do the last one. You got a 2 in everything. The 2's go away. Yeah, that's right. I don't know what the answer is. X is 5 and Y is 12. Let's see. That's the last step. Use that original to get it. 144 plus 25 is 169. The square root of 169 is 13. 13. You should get 46 over 13 as your final answer. Ready? I'm not showing you the answer until I see everybody's answer. What's that? That's the key. Did you find this? Oh, beautiful. Okay. Who else is working on it? Yeah, we just have to simplify, huh? Start dividing by 2. Yeah, divide by 2 once. Got it. Good. Fantastic. So we get 2z. Oh, I don't like red right now. 2z dz dt equals 2x dx dt plus 2y dy dt. Do yourself a favor. Divide everything by 2. We got x is 5, dx dt is 2, y is 12, dy dt is 3. The only piece of missing information I have is the z. We get z squared equals 5 squared plus 12 squared. We will pretty much be giving you situations where we have nice right triangles. If you remember the 5, 12, 13 right triangle, we'll see 3, 4, 5 often. 5, 5, root 2 kind of thing like that. And this is 13. Do the math, you get 46 over 13. Okay? If we're comfortable with those, we're on our way to tackling these calculus word problems.